Hi everyone, welcome to Module 8 for Kines 7103, Design and Analysis 1, which is taught in the Department of Health, Kinesiology, and Recreation here at the University of Utah. In this module, we're going to be talking about categorical predictors and how we can represent those categorical variables in a general linear modeling framework. So in the first part, we're going to be talking about a situation in which we only have two groups, making our analysis an independent samples t-test. But in subsequent videos, we'll also get into situations where we have more than two groups, which would make it equivalent to a one-way analysis of variance or a one-way ANOVA, right? But in general, what we're going to be looking at in this module and over a series of videos is understanding how we can represent categorical information in the general linear model and how we're going to actually get regression outputs that explain our data and how can we draw statistical inferences from those regression outputs. So thus far, we've looked at relationships between continuous predictor variables and continuous outcome variables. But now we're going to shift our focus to categorical predictors and continuous outcomes. So these categorical predictors might be natural groupings. So for instance, we might have, like in a cohort study, smokers and non-smokers, patients with a disease versus healthy controls, right? Or we might have males and females. There might be natural categories into which people fall and on which we will analyze our data. However, these could also be, and probably often will be, experimental groupings, right? So if I'm designing a randomized controlled trial, I might randomly assign people to the control group or the experimental group, or I might randomly assign people to more than two groups if I have a design where I have multiple levels of the factor. These categorical variables can also be made, right, if we take a continuous variable and sort of break it apart and force it to be categorical. So we'll look at an example of that in one of our later videos where we take people's 800-meter run times and then split them into slower and faster people. I think it's useful to do that in this instance because that's kind of illustrative of how we're transitioning from continuous to categorical predictors. However, I also want to caution you that breaking a continuous variable into a categorical variable is generally bad practice and has a negative effect on statistical power. So most of the time, if we have a continuous variable, we're going to want to keep it continuous because otherwise we risk sort of throwing information away if we take something that has a lot of variation in it and we break it into only two rough categories. So we'll do it in this instance because I think it has some educational value. But in general, if you have something that's continuous, you're probably going to want to keep it continuous. Okay, so the first major question that we have to address is how do we actually represent a categorical variable within the general linear modeling framework? So to do that, right, we have some sort of categorical factor. So in that case, we have our factor is were you a smoker, right? And we have level 1 of that variable is our smokers. Level 2 of that variable is our non-smokers. But this is fundamentally non-numeric. So what do we do? Well, the book recommends making contrast codes, right? And contrast codes are a little bit tricky to understand, but all we're really doing is assigning a numeric value to each level of this variable. All right, so that's when we talk about these lambdas. The lambdas are actually the codes that have k numbers of levels. So if we have smokers and non-smokers, in this case, k is equal to 2, and the value of the code is the lambda. So in x1, right, so here if we map this code onto our data, we'd have an actual x variable where all smokers got a +1, right? So lambda for smokers is +1, lambda for non-smokers is -1, and the sum of those lambdas is going to be 0, right? So note that this is the sum of the lambdas, not the sum of the data. But the sum of lambda 1, right, is 0. Now, if I do lambdas of +0.5 and -0.5, right, so lambdas for smokers is +0.5, lambdas for non-smokers is -0.5, I can map those codes onto my data to create x2, right, and that lambda code is a contrast code because the sum of the lambdas is 0. Positive 0.5 minus 0.5, it all totals to 0. Now, in the final situation, though, if I code these things as 1 and 0, right, my lambda 3, in which smokers get a 1, non-smokers get a 0, that is not a contrast code because 1 plus 0 is 1, right? So I have two contrast codes in my first two columns, and then in my third column, I have what we would call a treatment code, or what some people refer to as a dummy code, in which one level of the variable takes 0 and the other level of the variable takes a 1. And again, the thing I want to emphasize here is that this contrast coding is based on the sum of the levels, right? Not the sum of the data. Because if I add all these up, I actually have one more smoker than I do non-smokers. So the sum of the x's is 1, right? But again, it's the sum of the lambdas that's critical. So sum of the lambdas is 0 here, even though the sum of x's is 1. So this is a contrast code. The sum of the lambdas is 0 here, even though the sum of the x's is 0.5. So that's still a contrast code. Now the sum of the lambdas is 1, and the sum of the x's is 5 on this third one. So this is not a contrast code. And in fact, this is a treatment code, or what people refer to as a dummy code. Now, these are both valid methods of coding our data, and they will both lead us to the correct statistical conclusions, but we have to be careful about how we interpret our slopes and our intercepts depending on what codes we use. So in contrast codes, the levels of our code all sum to 0, and this becomes then equivalent to mean centering a continuous variable, right? It allows us to interpret y on average across levels of x, right? Because the intercept then becomes the average value of y, because the intercept is the value of y when x is 0. So if I have this code, right, where I have smokers and non-smokers, 0 is right in between those two codes. So my intercept is going to be the mean of my two groups. Okay, so it would be on average between the two groups. What is the value of y? Similarly here, if it's coded as 0.5 and negative 0.5, 0 is still right in the middle of those two codes. So my intercept would be the value of y when x is 0, which is to say that's the value of y on average between the two groups. So we get that benefit of contrast coding. Now with treatment codes, the levels of the code don't sum to 0, and one group is coded as 0 across all levels of the code. This is more analogous to having an interpretable 0 maybe in your continuous variable, right? So for instance, we talked about altitude has a meaningful 0 point when we use it continuously. Similarly, maybe we want to make non-smokers our reference group, and we want to understand everyone else relative to non-smokers. It might be actually useful to have a treatment code, because for instance, if we were doing a simple regression in this situation, then the intercept is the value of y when x is 0. Well, x is 0 for non-smokers, so our intercept becomes the predicted value for non-smokers, and then we'll modify that to make a prediction about smokers. So we're going to focus on contrast codes because they have a number of computational and interpretational advantages, but treatment codes and dummy codes are still perfectly legitimate methods of coding that'll get you to the correct answer, but you just have to remember which one you're using and how that's going to affect the interpretation of your data. So next, let's get a little bit of practice actually using these contrast codes. We'll do a lot more of this in lab, but we can visualize some of this now using the example from the textbook. So in the textbook, they proposed this problem where we wanted to test the efficacy of an SAT prep course, right? So we have 10 people assigned to take this course, 10 people who don't take this course, then they all take the SAT and we get their scores. If we want to look at the efficacy of this prep course, we're looking at SAT scores as a function of some intercept and a slope, right, times whether you took the test course or not, compared to a Model C in which the effect of group is omitted. Now we can write that a little more clearly if we actually spell that out and say in Model C what we're literally predicting is that the effect of group is 0, right? So regardless of what group you're in, x gets multiplied by 0 and goes away, right? Computationally, that's the same as omitting x from the model, but I like writing that 0 because it makes it a little more explicit that we're actually conducting a null hypothesis significance test for the slope. And in Model A, we're allowing for some non-zero effect. And if Model A leads to a statistically better fit of the data than Model C, we'd say that we reject the null hypothesis, and we think there's probably a non-zero relationship in the population. So in order to do this model comparison, right, it's first good to think about what are our codes that we're actually going to be using. So we're going to create a new variable, we'll call that x1, in which we apply the different levels of our code based on which group you're in. So in this case, if I have lambda for people who took the course, that's +1. Lambda for people who didn't take the course, that's -1. And then I apply those values for everyone who took the course and for everyone who didn't take the course. And what this coding scheme will ultimately get us is two different equations, right? We'll have one equation for people who took the course, in which their SAT scores are a function of an intercept and a slope times +1, and one equation for people who did not take the course, in which case their SAT scores are a function of an intercept and a slope times -1. And again, this is a contrast code because the sum of our two lambdas is 0. So by contrast coding that variable, what we can get then is a model A that we want to compare to model C. But first we're going to calculate our model C so that we can get a sum of squared errors for model C. So in model C, right, there's just this intercept, just a beta 0. And so when we fit that, we get a value of 591, which is, of course, the mean of everyone's SAT scores, right? And remember, if we only have one value, or if we only have one number to work with, the number that produces the smallest sum of squared errors is always going to be the mean of all the observations. So in the absence of any other information, 591 is going to give us the smallest sum of squared errors. So in model C, we estimate 591 for everyone. Now, in order to calculate the sum of squared errors for model C, we take the difference between each person's SAT scores and our model's prediction, and we get an error score. So here we get a column of error scores. We can then square those, and we're then going to add all of those error scores together to ultimately end up with the sum of squared errors for model C, which in this case happens to be 19,980. We can then contrast that sum of squared errors in model C with a sum of squared errors from model A. So in model A, we're going to be predicting people's SAT scores as a function of an intercept and a slope times our contrast-coded variable, which tells us which group you were in. And when we actually fit this using R or SPSS or whatever program, we get an intercept of 591 plus 14 times X. And what this then leaves us with is a unique estimate for each person in each group. So for everyone who took the course, right, they're going to have an intercept of 591 plus 14 times 1, which gives us 605. So that's 605 is our estimate for everyone in that group. For everyone who didn't take the course, it's 591 plus 14 times -1, right, or 591 minus 14, which leaves us with 477 for everyone who didn't take the course. Now, these two variables happen to be the mean of the SAT scores for people who took the course and the mean of the SAT scores for people who didn't take the course. And the reason why we end up with the means of those two variables is that we're using a least squares method of estimation, right? And recall that the mean always produces the smallest sum of squared errors for any set of numbers. In Model C, we only had one set of numbers, the total data set. Here in Model A, we have two sets of numbers. We're making a separate prediction for people who took the course and a separate prediction for people who did not take the course. So 605 will give us the smallest sum of squared errors of any number in this group. 577 will give us the smallest sum of squared errors for any number in this group, and therefore that'll leave us with the smallest total sum of squared errors when we add all of these things together. And again, to calculate the sum of squared errors for Model A, right, we take each actual observation minus the predicted value in Model A to get an error score. And then we can square those error scores and add all of those squared errors together in order to get the sum of squared errors for Model A, which happens to be 16,060 in this situation. Now, before we actually go through our ANOVA table to calculate the F statistic and a p-value, we can look at what this sort of looks like and get more of a conceptual understanding of what our model is doing. So in the fitted Model C, right, we have 591 is our estimate for everyone. So we're estimating one flat line, and regardless of which group you're in, right, whether you didn't take the course over here at -1 or you did take the course over here at +1, everyone gets the same estimate. And then we can calculate the distance from each data point to the line to get the error score. We can square that error score and add all of the squared errors together in order to get the sum of squared errors for Model C, which is 19,980. Now in Model A, we get a more sophisticated method of prediction, right, because we're allowing the prediction to change as a function of what group you were in. So when x is 0, right, when our x-axis is 0, we estimate the average SAT score between the two groups. So it's the average of people who didn't take the course and the average of people who did take the course averaged together. So that's going to be 591 right here in the middle. Now, for people who did take the course, they're coded as +1. So we go one step in the positive direction, and y increases by 14 points, right? So that gives us the mean of people who did take the course. Similarly, for people who didn't take the course, we start at 591, but they're coded as -1. So we take a step in the negative direction on the x-axis, and we lose 14 points, right? And so we go down 14 points to get the mean of people who did not take the SAT course. So by fitting this model, we actually estimate the mean for both groups, and we can draw a line between those 2 points, which has an intercept of 591 and a slope of 14. And that leaves us with a sum of squared errors for Model A of 16,060. Now, if we actually want to make a statistical inference about this reduction in error, we have to complete, our ANOVA table. So we have our total error, right, from Model C. This is essentially the amount of variation in Model C that we had to work with from the beginning. And then we have the error left over in Model A. And then the error explained by the regression is the difference between those two scores, right? So 19,980 minus 16,060 means that we effectively explained 3,920 squared errors with our model, but we have 16,060 left over. We can then insert the appropriate degrees of freedom, right? So this is parameters in Model A minus parameters in Model C, the number of observations minus the parameters in Model A, and the number of observations minus the parameters in Model C. We can then divide these across to get the mean squared error, right? So we're dividing the sum of squared errors by the appropriate degrees of freedom in order to get the mean squared errors. And then the F observed is the ratio of the two mean squared errors, which is ultimately 4.39. And using a statistical program, we can actually get the probability of observing that F under the null hypothesis, and the probability of getting an F observed this large or larger with 1 and 18 degrees of freedom is 0.0505. So although this is quite close under a strict null hypothesis test with an alpha of 0.05, this would not be statistically significant. Now, obviously, the situation might get a little more complicated than that, right? If you had selected a different alpha value, or if you had, empirical evidence to suggest the efficacy of these courses, right? The exact way in which you interpret this p-value might change a little bit, right, in terms of the strength of the evidence against the null hypothesis. But in a strict null hypothesis significance test, this p-value is greater than 0.05. So assuming we had set alpha to 5%, we would conclude that this is not statistically significant, and we could not reject the null hypothesis. This is an F observed that could have arisen under the null hypothesis due to sampling variability. It's not statistically unusual enough for us to really sit up and take notice. Now, we can get this statistical summary more directly out of R, right? So we apply a linear model where we're looking at SAT scores as a function of the course that the person took. Here you can see we get those estimates for the slope, or sorry, for the intercept and for the slope that we just went through. We can actually get a statistical significance test for each one. And then we can also get our omnibus test, right, where we get the proportional reduction in error. We get the F statistic, and we get the p-value for the model as a whole. So again, just to kind of go over what we're actually looking at here, when we have this F statistic, this is the omnibus F for the full model. So we're comparing all of our Model A where we have an intercept and a slope being estimated to a Model C in which only the intercept is being estimated. Similarly here for the effect of course, right, where we're estimating a Model A and where we have a beta for the intercept and a beta for the slope compared to forcing the slope to be 0, right? So we're conducting a null hypothesis significance test for the slope. And you'll notice that in this simple regression case, these values agree, right? Because we're comparing the same two models, which means we end up with the same p-value, and the f value here is really just the t-value squared, right? Because these are asking the same model comparison question. In situations where our models get more complicated, these will disagree, because the omnibus f-test is going to test everything, right, in model A, compared to a model that just has an intercept in model C. Whereas in a multiple regression, right, we're comparing just this particular slope. In this situation, we only have the one slope, so these two things are going to produce similar results. Now, we can also do a statistical test for the intercept, right, which is what R is doing here. And here are the models that we're comparing in order to do a null hypothesis significance test for the intercept. And we can see that having on average, we had SAT scores of 591, which was statistically different from 0. So perhaps not a really interesting question to ask of the intercept in this situation, right? I don't really know if you can get SAT scores of 0 to begin with, but our participants in this sample were scoring reliably higher than 0. However, depending on where we set our alpha value, we couldn't conclude that taking the SAT prep course actually had a statistically significant effect on your performance. So how do we get those estimates, right? At the moment, we've let the statistical program calculate them for us, and we probably will in the future, almost all of the time. But in the next lecture, we do want to walk through this process in a little bit more detail, showing you how we actually calculate these estimates for the slope and the intercept, and where we actually get those numbers from. The most important thing to understand, though, is that we're still using least squared estimation in exactly the same way that we've done before. So we're going to come up with values for an intercept and values for a slope that will give us the smallest sums of squared errors, and then we can compare the sums of squared errors in model A to model C in order to test the statistical significance of the f observed.